All right, we're going to move on now to Dave Huston, who's waiting in the wings. And Dave is going to talk to us about lead isotopes.
So I'm going to talk about lead isotopes in ore deposits, and I'm actually going to look at it in a different way to most everybody else. And then I'm going to look at distribution in terms of 2D space, because we actually see some interesting patterns when we look at lead isotopes and contour them out over two-dimensional space. But before I move on to that, I'd like to make a couple of acknowledgements. First of all, Dave Champion, who's a colleague, and he actually pioneered this idea of looking at isotopes in space, looking at neodymium. Also, Graham Carr, who is sort of the guru of Australian lead isotope analyses, and also Shen-Su Sun, who was one of the leading lights. So we'll start out. Okay, we'll start out and look at the uranium-thorium-lead isotope system. Like the osmium-rhenium system, we're looking at a radiogenic isotope system, and we're looking at the decay of uranium and thorium to lead. Now, we actually have 4 stable lead isotopes. One of them, lead-204, is primordial, and 3, 206, 207, and 208 are primordial plus radiogenic, where the 206 is the decay of uranium-238, 207 is the decay of uranium-235, and 208 is the decay of thorium-232. Now, to look at the data, we actually normalized the 3 radiogenic isotopes to the primordial isotopes. So we're looking at ratios of 206 to 204, et cetera, et cetera. So the other thing which is important to remember is that most of the data analysis that I'm going to be talking about, and what a lot of people do, is just looking at what we call the initial ratios. That is, the ratios at the time of ore formation. As you might imagine, if you analyze a mineral and it has a little bit of uranium in it, in addition to the lead, that the lead concentration of the various isotopes actually increases because uranium decays. What we want to do is take that away and just look at the initial ratios. And we do that mostly by looking at lead-rich minerals or samples. And as a general cutoff, we use about 1,000 ppm as a cutoff. So if it's above 1,000 ppm, we're looking at a lead-rich sample. And the important thing is that the initial ratios of the ore actually reflect the ratios of the sources at the time of lead extraction. So we're actually not looking specifically at the mineralization, we're looking at the source of the mineralization when we're looking at these lead isotopes. And the other thing is important that most of the common lead sources are from the upper crust and the basin. So we're actually looking at a model of the upper crust. Okay, so this diagram here is a typical lead-lead diagram where we plot 206 on the bottom, 206 on 204 on the bottom versus 207 on 204 along the side. And it just shows you the distribution of the data from all around Australia. Okay, so that's what all the little dots are. And you can see there's some nice trends in there, and there's clusters of data. And it actually tells you 2 things. And it tells you something about age and also what we call mu. And what I've done on top of that is I've plotted a number of lines, which are evolution models. Okay, so it's the evolution of lead as the uranium decays in this case. And that's actually a function of, well, there's the primordial ratios you see down in the lower part. It's a function of age and something we call mu. Okay. Now, uranium and lead actually fractionate slightly differently within the crust and between the crust and the mantle. And as a consequence, the uranium to thorium ratio actually changes depending on how much mantle versus how much crust is entrained within the particular sample you're looking at. So the variations in mu actually reflect the geochemistry of the source, i.e. whether it's more mantle derived or more crustal derived. And it turns out the lower end of that green double arrow indicates more of a mantle signature, whereas the upper end indicates more of a crustal signature. So we can use it in the same sort of manner as we use as the osmium isotopes that Bruce talked about a little bit earlier. Now, if you'll look at this diagram, you'll note that there's actually quite a large cluster of samples which actually give future model ages, i.e. the model ages are less than 0. And that's actually the result of two things. First of all, you can have lead growth after crystallization. And so if you have a very uranium-rich sample and you produce a lot of radiogenic lead, you can actually produce very radiogenic analyses which give you future age. And the other way you can do that is something called J or Joplin type lead, and that applies mostly to Mississippi Valley type deposits. I'd like to point out that right now we have about 8,000 analyses in our database, and this just shows all of the data from Australia. Now, if we go and take out all the lead core samples and look at the initial ratios, we have about 4,300 analyses, but as you can see, the amount of the data becomes cleaner. Okay, so you can see the same trends. The first thing you'll note is that most of the anomalously young or the future agers have been removed, just leaving the J-type lead, and that actually defines that sort of line that you can see, and which is I've just highlighted in the blue, and that all relates to Canning Basin MVT ores. That's what those samples are. So there's something very special about how those things formed. We can actually get 3 useful parameters from this data. Okay, the first thing we can do is get the model age. So we've got the model age is shown on the grid there. We can actually calculate a model age. Secondly, we can get the mu value. Okay, and that's that green arrow I showed you before, which indicates whether you're looking at a crustal source or a mantle source. And the other thing that you can get is something we call delta T, which is actually the mineralization age, where you have it, minus the model age. And that actually tells you some interesting things, and we'll look at that later on. Okay, so I'm going to first of all talk about lead isotope model age. And this is some work following along from Ralph Thorpe's analyses from the Abitibi-Wawa sub-province in Ontario and Quebec, Canada. These are Archean rocks, and they contain Archean volcanic-hosted massive sulfide deposits. And so what I've done is plotted model age versus the true age of the mineralization. And true age we've taken, since they're VHMS deposits, is the actual age of the volcanic rocks that they're hosted by. And you can see there's a reasonable correlation between the model age and the true age of mineralization. In fact, about 80% of the model ages are within 10 million years of independently determined mineralization ages. So it actually works. But there are, as we say, only 80%. There are a few analyses which are disturbed, which means something else has happened subsequent to the deposition of the deposit. So we can actually use lead isotope model age. And the important thing is if you have a very well-constrained local model, and that's what this is, you can actually produce very, very high quality ages, but you do still have to have a bit of taken with a grain of salt. So now we'll move on to a second thing and look at how you can actually determine lead sources. Okay, and so we're going to go down to Tasmania. And this is some analyses. This is just fields of analyses that we've done looking at data from Western Tasmania. So we have the Oceania deposit, some Devonian lead, zinc, silver veins, and also the Renison deposit. And if you look at the Renison samples in this area here, you see there's 2 groups. There's the ones that are directly associated with tin mineralization, and also some late stage galena veins. Now it turns out that these things are very, very close to each other. In fact, they're pretty much within air. But the important thing is that we took some analyses from the Pine Hill granite. We took feldspars from the Pine Hill granite, which can give you initial ratios. We analyzed those, and it actually tells you that the lead isotope characteristics of the Pine Hill granite are identical within error of the lead isotope characteristics of the Renison ore bodies. And since the Pine Hill extends to within a kilometer of the Renison, the Pine Hill granite extends to within a kilometer of the Renison deposit, we're quite happy that the Pine Hill was a source of the lead at Renison and probably also the tin. That's exactly what we expected, but it's nice to have confirmation. So now we're going to move on and look at things spatially. And so we're going to concentrate mostly on the east coast of Australia. And this diagram just shows you, in effect, the Tasmanides, going from Tasmania all the way up to the tip of Cape York. And what we're looking at is the mu. Okay, that's the 238 uranium on 204 lead. And the high mu, i.e., those associated with more crustal type rocks, has the reddish or the warm colors, whereas the low mu, which are associated with more juvenile type rocks or lead, is with the low, the blues and the greens. And you can see there's some patterns in that data across the entire east coast of Australia. And it's just like a few that I'd like to highlight. First of all, if you look, and I'll just go back, whoops, and just highlight, there's a little red line here, which actually marks the boundary between the eastern and central Lachlan. And you can see there is actually quite a difference in lead isotope patterns across that boundary. So we're actually mapping the tectonic boundary using lead isotopes. It also, and I'll just highlight that again, if you look at the little blue zone in there, that actually is the Macquarie copper-gold province. Very well maps the Macquarie copper-gold province at this scale. It also maps the extent of the Wagga tin province. Okay, so the Wagga tin province is characterized by high mu lead, which is perfectly consistent with the more evolved signature of that particular province and what you'd expect from a tin province. It also maps the boundary between the New England origin, shown in here, and the Thompson and Mossman origins and Lachlan origins shown in here. So so you can start to see some differences tectonically. The other thing is, at a more local scale, it identifies the Moisten Fault as a fundamental boundary between the Stawell and the Grampian Staveley zone in Victoria, and that's shown in this little area through here. And it also shows you quite a complex structure in the New England origin. And we see a similar sort of pattern in the neodymium model ages, and it actually corresponds quite well to the ore cline that's been mapped in the New England area. So now we'll move on to something different, and we'll look at the delta T, which is as you recall, the difference between mineralization age and model age. So it's telling you about different lead sources. And again, the high delta T is warm, and the low delta T is cool. And we can actually relate these to different tectonic elements within the convergent margin system that has happened since the Cambrian in Australia. And it turns out that the warm colors are associated, we think, with the subduction of the Proto-Pacific plate, whereas the cool colors, the greens and the blues, are actually associated with Proto-Australia, because we have two different styles of lead between those two tectonic environments. So there's a general decrease in delta T from east to west. So greens here, reds and oranges here. And there's which we interpret as the increasing influence of the Pacific, Proto-Pacific plate to the east. There's also zones of high delta T in Western Tasmania, shown in here. And that's actually different from Eastern Tasmania. And also the Southern New England origin in the Hodgkinson province up in here. So it's telling you something about the source of the metals or the source of the lead in these systems, and probably something about the tectonic evolution of these systems. The other thing which is important, which is actually at the time we were doing this analysis was quite important, is because we were looking at, you know, whether the Staveley volcanics, which are sitting over in here, are the same as the Mount Reed volcanics over here. And you can see from the lead isotope data, it's not consistent. The other thing is that the Macquarie arc is shown here as being red. It's actually indicating perhaps a Pacific plate associated with that. And we'll just show you a model for this. Okay, so what we have is a proto-Pacific plate to the west, a proto-Pacific plate to the east, with the proto-Pacific plate being subducted. We have a small continental fragment with proto-Pacific type lead. It has a higher mu and a delta T of about 200 million years. You're subducting that along with its the slab, which has a similar delta T value, but a much lower mu value because it's more juvenile. And you bring that underneath the proto-Pacific, proto-Australia continental crust, which has a high mu, and it has a delta T of around 0 per mil. Okay, so you're looking at a 4-component system when you also include the mantle underneath Australia. So you can actually account for the lead isotope signature that you see in Eastern Australia in this sort of environment where the proto-Pacific plate is actually produces the low delta, the high delta T values, whereas the proto-Australia continental crust produces the sort of normal things. But the interesting thing about this is if you melt the subducting slab or the mantle just above the subducting slab, you're actually going to produce a signature with a proto-Pacific type of lead. And that's actually what we see in the Macquarie arc and the porphyry copper systems associated with the Macquarie arc. And so you can actually use the lead isotopes to understand the tectonics, but also to predict the style of mineralization that you're going to have. And to follow this along, so what we did was we actually looked at the mu values in the New South Wales and the Golden Ridge. So this is a diagram specifically constructed for New South Wales, just illustrating the variations in mu values. So again, the red indicates low mu, whereas the blue indicates high mu. The color ramp is reversed to what we saw before. But if we actually look at this, and I've plotted the distribution of major gold deposits in different colors, and indicating the different style of deposits and the different sizes of the deposits. So if you actually take that and we actually take out and determine the mu values for all the deposits, and then look at the contained gold, we see that the largest gold deposits in New South Wales are strongly associated with the very juvenile crust. Okay, whereas if you go to lower, smaller deposits, they're associated both with the juvenile crust and the more evolved crust. So if you were looking for the larger gold deposits in Australia, you would be wanting to go to the more juvenile. In New South Wales, you want to go to the lower mu values. The other important thing is that these low mu values include porphyry copper gold, i.e. the Macquarie arc porphyry copper gold deposits, epithermal deposits, and also the McPhillamys deposit, whatever that is. So it actually applies on a number of different deposit types, and it's a more of a generic tool there. And the question becomes, is there a gold link to the subducted Proto-Pacific oceanic crust? Okay, now we're going to move on to Northern Australia or northwestern or northeastern Australia, and we're going to actually look at the Mount Isa province in northwest Queensland and southeastern Northern Territory. And we're going to just look at some lead isotope variations in that. And why do we do that? Well, there's 113 million tons of zinc, 69 million tons of lead, and 9.9 million tons of copper endowment. And it turns out that 69 million tons is about approximately a quarter of the world's total supply of lead. So it's actually a very major metallogenic province. Okay, so the light blue dots, which is what we're going to concentrate on here, are the HYC or MacArthur-like deposits, and they actually define a north-northwest to northwest trends, and you can just see that on that blue line. Okay, I want you to hold that blue line in your mind as we move through this talk, because it actually is going to crop up a few other places. Okay, the important thing is that the trend cross-cuts the geology, which you can see here. You can see it cross-cuts the structures. It also cross-cuts a lot of the lithological boundaries. And it also cuts across the geophysical grain. And I haven't shown that at this point. So now we're going to look at the lead isotopes. And so this is the same area that we looked at before. And these are lead isotope analyses. And you can see there is actually quite a strong gradient in here with the north-northwest trend, and it trains into a northwest trend. And if we actually put the deposits on, we actually find that Tick Hill, Isa, Loretta, Century, Walford Creek, and HYC actually plot along that gradient. Okay. And if you look at in detail, there's a lot of complexity within that lead isotope signature. And that might relate to some of the structures that you can see. And again, that trend that we talked about before. Okay, so that's the lead isotopes. And so we actually looked at that, and Carl Charnada, who is a colleague of mine, actually saw that and said, well, what about some other parameters? And so he actually looked at the lithospheric asthenospheric boundary. And this diagram shows you it's the depth of the base of the lithosphere is what we're looking at. And you can see there's actually a relationship between the deposits, which are shown here, here, and here, and the 170-kilometer contour of the LAB boundary. Okay, so we're seeing it in two different data sets. And you can see the same trend there. Actually, we can see it in a fourth data set, and this is gravity data. It's 30 kilometers upward continued. And you can see there is a trend, okay? And all those deposits are located along it. And you see the same relationship in the 15, 50, and 100-kilometer upward continued images. Now, we weren't the first ones to see that. Bruce Hobbs argued that there was a gravity worm that connected all these deposits. I think we're seeing the same relationship here in this data, in the lead isotope data, in the LAB data that Bruce saw 20 years ago. Okay, not only does this work in Mount Isa, but you can actually see a lot of deposits elsewhere in the world are actually associated with mu gradients. And here we go to Ireland, and this is some data from Steve Hollis. Yep. And anyway, he's plotted and done a mu map and shown that the major deposits in the Irish zinc belt are actually associated with a gradient in the mu values. Okay, the same thing that we're seeing in Mount Isa, you're seeing the same thing in Ireland, but also in North America. So this diagram here is a mu map where we go from juvenile to evolved up and through here. And as you can see, the major deposits shown in the blue are associated quite strongly with that, the break between the sort of the yellows and the browns that you can see quite strongly through there. But moreover, if you look in detail here and here, the actual deposits are associated with complexities within the lead isotope patterns, much the same as what you saw in Mount Isa. So we actually can see the same patterns in 3 different areas around the world. The other thing is that the LAB contour also shows a good relationship with the deposits that you can see here. And the LAB relationship holds globally. Okay, the last thing I'm going to talk about is a direct exploration use. Okay, and this is as a vector in the Zeehan tin-lead mineral system. This is in Zeehan in Western Tasmania. And this is just a mu map. And I'll just go through this. So first of all, the Zeehan field is strongly zoned, and it contains both tin-rich and zinc-lead-rich deposits. And so we have the tin deposit at Queen Hill, and then all these other little dots are lead-zinc deposits. Okay, lead-zinc-silver deposits. Okay. The other thing is that the Queen Hill deposit is sitting on a whaleback of the Heemskirk granite, and this is the 2-kilometer isotope map. And you can see it actually sits there on an apophysis of the Heemskirk granite. And you can also see that the lead isotopes actually zone away from the Queen Hill deposit. So you're actually looking at a mixing between low 206 on 204 granite-derived lead with high 206 on 204 ambient lead. So it suggests that you might be able to use directly the lead isotope signature as an exploration vector. So in conclusion, the lead isotopes actually provide vectors to ore at the continental, province, and district scales. It provides indications of metal endowment at the province scale. I haven't talked about this. It can map and identify tectonic boundaries in provinces. It can provide direct evidence of metal sources, and it can constrain the age of mineralization. And so with that, I'm finished.
Thank you so much, Dave. That was fantastic. I know that I've seen a lot of the lithosphere boundary work that GA has done, and Carol and yourself, but not in association with the gravity data as well. So, so that was particularly interesting to see. I was wondering if you can compare the data that you've got for lead isotopes, which I think the data that you've been showing is in rock samples, or galena?
It's galena.
In galena. So in a few of the talks we've seen people looking at isotopes in groundwater. So can you comment on what the isotope systems might do in groundwater around an ore body for lead?
Well, I would expect that you would see an influence of the lead isotope of the ore bodies around the deposit. So, and I think it's been proposed before that you can use lead isotopes of groundwaters as an exploration vector. So you're actually looking for anomalies, and so you look for less radiogenic lead in this situation, because that would be the initial lead that you see in the ore bodies, whereas the groundwater that's circulating with sort of normal rocks would have more evolved lead. So it's definitely possible that you could use the lead isotopes in that sense, and I believe that the CSIRO have investigated that.
I know GA is collaborating with CSIRO, aren't they, on a very large hydrogeochem project, so it might be interesting to see if there was a pattern in the lead isotopes in that data set. Yeah,
I haven't seen that data yet, so I can't really comment. We are also doing a collaboration with a PhD student at Melbourne Uni looking at the lead isotopes of our sediments. So that's also an interesting thing that we'll be curious to see the results of. And I think that could be quite interesting.
Rick, did you have a question?
Yeah, I mean, it's always really, you know, that pattern is so interesting and really intriguing to see it repeated in a number of different areas in almost all of the areas you showed, maybe except the Irish Midlands. The sampling is just extremely irregular. Like if you were doing a resource estimation, people would say, forget it, you don't have the right points to do any sort of a contour map over top of this. And if you look at those points, you might argue that that any number of contours could be possible if one was going to be, and I'm not saying that you're doing this, but if one was going to be seeking a solution or applying a cognitive bias. And I'm not, and like I say, I'm sincerely not saying you're doing this, but there are tests to actually to prove that that hasn't happened. And have you ever done that for, say, the lead isotope data running from Tick Hill up to HYC to say there's no other way to slice up this data in a contour map than the way we've done it?
Okay, the contouring was done using natural neighbors in a GIS. So it's totally independent of our preconceptions. And in fact, we were quite surprised when when that data came out with that really strong gradient that we saw. And we realized there is an issue of number of data. And so what we've done is we've gone out and we sampled additional areas, additional samples to increase that data coverage. Unfortunately, we don't have the results back yet. And so hopefully the results will confirm what we're doing. If they don't, well, then we have to have another think about it. So we are doing that. We have not done any sort of statistical test to verify that boundary, but I think that it will hang together. In terms of North America, Western Canada, which I guess is favorite, near and dear to your heart, there's another data set which is a large data set. It's a UBC data set. Now, unfortunately, these things are not digital, and so you actually have to go and physically type the data in. And so at the time, we didn't have the time, and because we're in Australia, didn't have the justification to go and do that. So it would be a worthwhile thing to incorporate the UBC data set into that thing, because what we used was Ralph Thorpe's data set from the GSC. And it's just a amount of probably 2 or 3 days to sitting down and typing the UBC data set in, or use some technique to get it in. And then hopefully that will increase the density of the samples we got. Unfortunately, lead isotopes, you have to have a lead-rich sample. And so you have to have actually an ore sample, well, a mineralized sample. So you're actually limited to where the mineralized samples are in terms of constructing a diagram like that. And there are inherent problems with it. And we recognize that. And I think the fact that other data sets are showing the same thing, and other data sets which are independent of well, they actually have a regular sampling pattern, gravity, and they tell you the same thing. I think that's actually important, and it supports the lead isotopes. Now, I'd be really unhappy if we went and put all this other data in and it falls apart, but it's possible, and we are testing that.
Yeah, thanks. Yep. Oh, that was. It certainly looks like it should work. I mean, it's. I'm not saying no, you completely made it up. I'm just.
Yeah. No. We realize the issues, which are perfectly legitimate, and we're trying to address them.
Great.
We have a couple more questions for you, Dave. One question from Azam says, is it possible to get lead isotopes from silicate minerals?
Yes. One of the things that you do is you can do K-feldspar, potassium feldspar, because it concentrates lead. I think it substitutes for the potassium, and it tends not to concentrate uranium. So you can actually get you can start to get initial ratios, and you can do that a couple of ways. They do a leach, where they actually leach out the radiogenic lead, because it's quite it's quite easy to get out. And then they analyze the residual, and that gives you the initial ratios. So that's one way to do it. You can also do laser ablation, which I'm told by Roland Moss actually works pretty well. The other thing you can do is a similar thing for clinopyric sinks, because they actually can contain a lot of lead. And that's the way you can get mafic rocks in terms of the lead. But again, these have to be very, very well preserved. So.
Thanks. And then Brennan Simpson is asking, what confidence do you have in the lead isotope data? How susceptible are these models to contamination and inheritance?
Okay. Well, we talked, the diagram that I showed, the model ages that Ralph Thorpe, that we calculated with Ralph Thorpe's model for the Abitibi-Wawa, you could see about 80% of the analyses gave the number that we expected, whereas about 20% had been disturbed. And so there is an issue about disturbance. Now it turns out that the disturbance doesn't affect or doesn't necessarily affect the mu value. Okay, and that's what we're contouring, is the actual mu value. And so you can actually have a disturbed lead isotope signature that doesn't affect its mu value. And what we try to do to resolve that is that we collect more than one sample from the same deposit, and we use the least radiogenic analysis, i.e. the oldest model age analysis, as the point that, as the data for the point that we plot on it. So we're looking at more than one point in most cases, although in some cases you can only get one sample. And yeah, that's how it works. It's not going to be perfect, but it works generally, and the patterns that we see are relatively consistent.
Awesome.
Okay.
Thank you.